Hello. In this video, we will learn about truss analysis using method of joins. Chapter 6, topics 6.1 to 6.3. Simple trusses, the method of joins, and zero force members. Today's objective is to define a simple truss, determine the forces in members of a simple truss, and identify zero force members. So what is a truss? So the structure of the bridge that you see in this photo here, that is called truss, where the links or linkages are called the truss members and the connection points are called joints, where the truss members are connected because of using fasteners or by welding. One of the assumptions used when analyzing a simple truss is that the members are joined together by smooth pins. So this connection points here and here, we can say that those are the smooth pins. That's our assumption. When using the method of joints, typically three equations, so correct answer is B, equations of equilibrium are applied at every joint. So our intention to our objective to solve the problem of trusses is that we have been given a structure like a truss and the externally applied load at the truss joints, and using based on those loads we would like to calculate the loads in each member of the truss, and then we would like to make sure that the design of the truss is safe such that each and every member has the load within the member which is uh, within the limits of the tensile or compressive strength of that member. And this is what we are going to do in this chapter. Application trusses are commonly used to support roofs, as you can see here. Now, for a given truss geometry and the load, how can we determine the forces in the truss members so that we can size them? So, if we have been given truss and externally applied load at different joints of the truss, and we would like to calculate the forces within each of this member of the truss, then we can apply truss force analysis. However, more challenging problem is that if we have been given the load that the truss should carry, how can we design the truss's geometry to minimize the cost? And there are multiple options available to design the truss geometry for the given loading condition, and this type of problem is more challenging. Applications, so you can see trusses are used in variety of structures like cranes, the frames of aircraft, or the space station. So these are a few examples of trusses. This is the frame. This is bridge. Now you can see here this arrows, they indicate the load that is applied. So this is bridge truss, and this is the bridge truss with the applied load, where KIP stands for kilopound. Now if we know all this different loading which is applied to the bridge truss, we would like to calculate the forces within each member of the truss and as well as at the joint, and we would like to make sure that those joints and the members are within the safe limit of the strength of those material. Another example of truss bridge, even the Eiffel Tower is also a kind of truss. Airplane and space station. So a truss is the structure composed of slender members joined together at their endpoints. So these are called members once again, and they are joined together at endpoints. And these black arrows, they indicate the externally applied load or the support reaction. For example, here, these two arrows are called support reaction, and here this arrow is the support reaction, while all other arrows are externally applied load because of the weight attached on top of the truss. So if a truss along with the imposed load lies in a single plane, then it's called a planar truss. So in this example, if we look from here on this side, then everything is in one plane. So that's called a planar truss. In planar truss, M is number of members, and that can be calculated using 2 times number of joints minus 3. So for example, here there are the 3 members, and there are 1, 2, and 3 joints. So 2 times 3 minus 3. So 6 minus 3 is 3. So number of members is equal to 2 times number of joints minus 3. Now there are certain assumptions we make before we apply analysis and design for truss. So when designing the members and joints of a truss, first it is necessary to determine the forces in each truss member. This is called the force analysis of a truss. When doing so, when doing this, two assumptions are made. Number one, all the loads are applied at the joints. The weight of the truss member is often neglected as the weight is usually small as compared to the forces supported by the members. And second, the members are joined together by smooth pins. This assumption is satisfied in most practical cases where joints are formed by bolting the ends together. And this is really good, one of the most important assumption that the members are always two force members, means the loads are applied only at two endpoints. Now, there are two types of loads that the truss members are being subjected to. Either they are in tension or compression. This point here is called joint. So when a member is in tension, then it pulls at the joint at both ends. So at this joint it's pulling, at this joint also it's pulling. When a member is in compression, it pushes at the joint. Now this is one example of the method of joints for truss force analysis. So here the truss is made up of three members, AB, BC and AC. And there are two supports. Support A is pin support and support C is called rocker support. So this rocker support allows some movement along horizontal direction, but it does not allow any vertical translation motion at joint C. And this truss is subjected to 500 Newton load at joint B. So if for the truss force analysis, we would like to know what are the forces in member AB, BC and AC, and are these members in tension or compression? So for that, we need to use, in method of joints, we draw a free body diagram for each joint and then solve for the forces. So starting from joint B, if we draw the free body diagram, then at B, 500 Newton forces apply horizontally, and then there are two members, FBA and FBC. We do not know what type of loading is applied to these two members, so we assume that member BA is in tension. So see, this arrow is pulling at joint or going away from jet, away from joint. That means the member is in tension. If the arrow is going towards the joint or pushes at joint, that means the member is in compression. So this is purely our assumption that this is in tension, this is in compression. And then it's a simple two-dimension force analysis problem where we have two unknowns, FBA and FBC, and we can apply three equations of equilibrium, that is sum of the forces in x equal to 0, sum of the forces in y equal to 0, and sum of the moments about b equal to 0. And by applying those three equations, we can calculate the value of both FBA and FBC. So when we solve the problem, and if we get positive number for each one of these forces, that means our assumption for tension and compression is right. If for one of the members we get the answer as negative load, that means the actual member is in the opposite type of loading than our assumption. Okay, and that is being explained here. So we have two equations of equilibrium, sum of the forces in x and y equal to 0, and then we used to solve for two unknowns. So because we have two equations of equilibrium, with method of joints, we can solve only up to two unknowns at a given joint. So the steps for truss force analysis, if the truss's support reactions are not given, then draw a free body diagram of the entire truss and determine the support reactions. This is what we learn in chapter 5. Draw the free body diagram of a joint with one or two unknowns. Assume that all the unknown members act in tension unless you can determine by inspection that the forces are compression loads. So pulling on the pin. Apply the scalar equation of equilibrium. This is again from chapter 2 and chapter 3 that we have learned. That sum of the forces in x equal to 0, sum of the forces in y equal to 0 to determine the unknowns. If the answer is positive, then the assumption is correct. If the answer is negative, then the assumption is the opposite. Repeat steps 2 and 3 at each joint in succession until all the required forces are determined. So for example, in this case, if we need to calculate the forces in all three members, then first we draw free body diagram for joint B and solve for forces FBA and FBC. And then we draw free body diagram for A or C and calculate the force in remaining member AC. So that's how we draw free body diagram for each joint and keep solving for the forces within the members and then move on to the next joint. And this method is called method of joints. Now, before we do that, there are certain members in our trust which do not carry any load, and those members are called zero force member. And there are two conditions with which we can identify zero force member in a given trust. So condition number one, so there are multiple members here that we can see. Now, this particular member A and D, those joints A and D, there are only two members connected. Okay, so AF and AB are connected at A, and DE and DC are connected at joint D. Now, when there are only, so condition number one or rule number one to identify zero force member is when there are only two members being connected at a joint, and that joint does not contain any externally applied load like this, or it does not contain any support reaction, then both of these members are called zero force member. So for this given truss, member AF and AB plus member DE and DC, they are all zero force members. Means the force within those members is neither tension or compression, it's exactly zero value. Now the question is, why do we have even them if they are zero force member? So the answer is they are zero force member only for the given loading condition. For future reference, if the loading changes and the load is applied at D, then they are no longer zero force member. So zero force member are not useless. Only for the given condition, they don't play any role. But when the loading changes, they may play any role. They actually they are important and they play the role in carrying those load. Okay, so we can simplify this truss by removing those four members and then apply the truss force analysis to calculate the forces in the remaining members. So that is rule number one. Exactly two members connected at one joint, and that particular joint does not contain any support or it does not contain any externally applied load, then both of those members are zero force members. Second condition or second rule to identify zero force member is when there are three members connected at the joint. For example, here, and two of them they are in line, then the third member is called zero force member if the joint does not contain any externally applied load or support reaction. So in this example, both member DA and CA are zero force members. Means even though they are there, they do not carry any load, so we can actually remove them from the truss structure and we can simplify it of only three members rather than five members. So once again, I repeat the condition that when there are three members connected and uh, two of them they are parallel or in line, then the third member is zero force member if the joint does not carry any load or any support. So the word for like in line is called collinear. When two of the members are collinear means they are in one line. Okay, so now in the next video we are going to solve a truss problem using method of joints. Thank you.